Hello, so in this video we're going to look at sketching gradient functions, or more specifically, if we got the graph of, let's say, y is equal to f of x, then how can we sketch f dash of x, right? Y is equal to f dash of x. So that's what we're going to be looking at today. So we're going to look at sketching the derivative graph given the original graph, right? So let's just recap what we've done so far, the main bits we're going to be using today. Well, firstly, we looked at increasing and decreasing functions. So in particular, if the derivative, the gradient is positive, then the graph, then y equals f of x, my graph, is increasing, right? And then conversely, when the gradient is negative, then y is equal to f of x is decreasing or going down, right? And also this idea about a stationary point, okay, where if the gradient was equal to 0, then it's a stationary point. Then x is a stationary point. So that could be a maximum, a minimum point of inflection. We looked at that last time. So as a very brief example, let's say we have this graph here. Let's say we have this graph here. Let's say that is and it has a minimum point of 4. And that's really it. Okay, so this idea about increasing, decreasing and stationary points. Well, firstly, we can see that the graph is decreasing before my stationary point, right? It's going down, right? That's in red, right? That part of the graph is going down, it's decreasing. Then when we get to our stationary point, the gradient is 0, and then it's increasing, right? It's going back up. So if I was to highlight that, then it's increasing. So that means we could say f dash of x, then the derivative is going to be negative when x is less than 4. Hang on, let me change my font. Okay, let me rewrite that. So the derivative, f dash of x, the gradient is going down before 4. So it's going to be negative when x is less than 4, as it's decreasing. And then when it reaches 4, f dash of x equals 0 at x equals 4, because it's a stationary point. Then after x is 4, it's positive, right? The gradient is positive after the curve is going up. And so we can use this idea about considering stationary points and increasing and decreasing parts of the graph to sketch, to get a good idea about what my derivative graph will look like. So yeah, I think it's best to jump into some examples then to see what we mean. Okay, so we're given a diagram which shows the curve with equation y is equal to f of x. The curve of stationary points at what? -1, 4 and 1, 0. So it would be there as well. And it cuts the x-axis at -3, 0. Okay. Sketch the gradient function. Okay. Showing any coordinates so it meets the x-axis, blah blah blah. So we need to sketch the gradient function y equals f dash of x. Now obviously probably you might be thinking, well, I need the equation, right? I need to find the equation f of x, and then differentiate and then sketch that, right? You don't have to if you're given the graph, right? We can get a very good idea about the gradient, what the gradient of the graph looks like, if the differential looks like, by considering my stationary points and the increasing and decreasing parts. Okay, you could do that. I mean, it looks like it'd probably be a cubic, right? So you could probably formulate a cubic equation. That you might be able to do that, but it'll take a bit more work. But what we're going to do is obviously we need to sketch the derivative function. Now, probably the best place to start with this, if we're gonna consider the differential, the derivative, is to consider my stationary points, which is here and here, right? Now, because they are stationary points, that means the derivative function y is equal to f dash of x has to be 0, or kind of like a root, right? So let's take this stationary point. That's when x is minus 1. So that means at minus 1, my gradient function will be at 0 here. Okay? And likewise, when x is 1, that's my other stationary point at 1 there. So if I plot my stationary points, those are my roots of my derivative, because the derivative will be equal to 0 at these stationary points, right? Okay, so we plotted my roots. Now, what we're then going to look at is considering the increasing and decreasing parts of my function. So firstly, it's increasing until it reaches my first stationary point. It's going up. So that means the gradient would be positive, right? So it's going to be in my derivative, it's going to be on the positive y-axis. It's going to be above the x-axis, right? And it's going to be positive, and then it's going to come down to my derivative, which is my stationary point. So that part of the graph is going to be coming down, right, to my point here. Okay, that corresponds to the yellow part I've highlighted, right? So that's my first part of the graph done. Okay, so that's my gradient until it reaches my stationary point at minus 1. What about after then? Well, then it's decreasing, right? It's decreasing until it reaches 1, and then it goes back up, right, to my next stationary point. So the gradient is decreasing, so it's going to be below the y-axis. It's going to be negative. Remember, in decreasing is where the gradient is negative. So remember, the gradient function, my gradient graph, will be positive if it's increasing and negative if it's decreasing. So now I'm on the red part, this part between the two stationary points, between minus 1 and 1, which means it's going to be below the x-axis, in the negative part. So it's going to look something like this. So if I continue the graph on, there we are. So it's basically going to dip, and then it's going to come back up, because think about it, my two stationary points will be the gradient at 1, right? The gradient would be 2 roots here. So the graph has to go and reach the 2 points here. So it has to dip underneath the graph and then go back up, okay? But it's still negative, right? So it's still decreasing because it's underneath the y-axis, underneath the x-axis. Now, after it reaches the second point, then the graph is increasing, right? So after that, it's going to be positive again. And there we are. And so that is my gradient function. And you can see this makes sense because this is a cubic. And when I differentiated it, I have a quadratic. Well, if we have a cubic x cubed, that would go to like 3x squared, right? That will go to a quadratic expression after we differentiate, right? So it makes sense. We go from a cubic to a quadratic, okay? So that is my graph. So to summarise, my two stationary points at minus 1 and 1 are my roots, because that's when the gradient is equal to 0. Then this part, then it's increasing until my first stationary point at minus 1, so it has to be above the graph, okay? Then between my two stationary points, then it's then decreasing my curve, so it has to be below the x-axis, so it has to be negative there. Then after the second stationary point, then it's going back up, it's increasing again, so it has to be above the x-axis, it has to be positive, okay, here. And so there we are. Okay, let's have a look at another example. And here we got this more complicated looking graph. Okay, we are told this diagram shows the curve of equation y is equal to f of x. The curve has an asymptote at y is equal to -2, which you can see there, and a turning point at -3, -8. It cuts the x-axis at -10, 0. Okay, sketch the derivative graph again, right? So again, we're not given the equation of this graph, so we can't really exactly work out the derivative and go and sketch it that way. We kind of just have to look at the graph and sketch the derivative from that. So again, we're going to draw a nice axis, and my first idea is to again plot my stationary point, because I know that a stationary point, my gradient would equal 0. Okay, so that means it'd be a root. It'd be on the x-axis. So my stationary point is x is -3 there. So -3 is now going to be on my x-axis. It's going to be a root because it's going to equal 0. Okay, for my derivative. Okay, now I'm going to consider the periods of my graph when it's increasing then decreasing, or vice versa. So firstly, before my stationary point, the curve is decreasing, right? Which means it has to start below the x-axis. It has to start in the negative part of the graph until it reaches my stationary point on the gradient. So it's going to come up like this, and then it's going to reach my stationary point, okay? Because it's going to be then on the negative part of the graph. It's underneath the graph, that's the negative part, because the gradient is negative there. After this stationary point then at -3, then my curve is increasing, okay? So it's going to then go above my graph like this, something like that, right? Hang on, I need there we are. But is it going to go? But is it going to go up like this? Is it just going to shoot up after? No, it's actually going to look something like it's actually going to come back down, and it almost tends towards an asymptote. Okay, why is that? Because if you look at the graph at the long term here, if you look at the graph at the long term, it's kind of leveling off towards the asymptote. So the gradient is kind of tending towards 0. The graph is flatlining as x goes to infinity, right? Right. So if you look at it, I can draw like a straight line, and that's my tangent. So it's kind of, that means the gradient, because the curve is leveling off here at the end, that means my gradient has to go to 0 at the end, okay? Because of that. So it's going to shoot up, right? So it's going to shoot up after my stationary point because it's positive, but then it's going to come back down and tend towards 0, okay? As that's when the gradient is flatlined, okay? And so yeah, so then you can see that then for part B, my asymptote is simply going to be, well, the x-axis, or what we say y is equal to 0, okay? Okay, and so there we are. Another way you could spot the asymptote is actually, well, y is equal to -2 is my asymptote originally. Well, think about it, you can think of that as a function of x, right? But it's a constant, right? If y is equal to 2, then dy dx, because 2 is just a number, it's just going to go to 0 after differentiate, which means my that means my gradient asymptote is going to equal 0 because the asymptote differentiates to 0 as it's just a number. So you can think of it that way as well, okay? And so that's what my graph will look like, okay? Cool. Okay, so let's practice with some more examples then. So I've got these two graphs here. I'm going to start with this one first. So, okay, let's draw a nice axis again. X and Y, part C. So again, we need to sketch the derivative function as if these are the original functions. Okay, so what's the derivative of these graphs? Well, firstly, again, we're going to consider the stationary point. So that's the easiest thing to plot. So I'm given a stationary point at 4, 3. It's a point of inflection because it has that sort of leveling off feature, right? So at 4, 3, so x is 4, that's going to then be my stationary point. That's going to be sort of a root then, because it's going to equal 0 for the gradient function. So it's going to pass through the x-axis at 4. Then we're going to consider the what's it called? The increasing and decreasing parts. So firstly, before my asymptote at x is equal to -7, the graph is going down, it's decreasing, right? But actually notice the graph kind of is leveling off, right? It's kind of leveled off at the start here. And then once it's sharply going down towards my asymptote. It's tending towards the asymptote. So the curve is going down more steeply, which means it's basically going to, again, be an asymptote. It's going to go down like this as well, right? Because the graph, obviously, because it's decreasing, it has to be on the negative space of my graph. It has to be in the negative underneath the x-axis because it's decreasing. But again, it's going to go more, it's decreasing very quickly. So it's going to keep going down to negative infinity. It's going to keep going down. And that's actually, it's tending towards the same asymptote, right? At x is -7. Now, why is that the same asymptote then? It will always be the same asymptote if it's x, okay? Because the idea is, what this asymptote is saying is, originally, x is not, the function is not defined at x is equal to -7, right? If I make a note, that's what an asymptote is saying here. If x is equal to -7, the function is not defined. So then if we differentiate it, then it can't be defined either. If the function is not defined, then nor can the derivative function. That cannot be defined either. So if we have an asymptote, if we have a certain value of x, we can't have originally. If we differentiate, we still can't have that same value of x. It will still be an asymptote. Okay. It's not a valid input, so that means it will have the same asymptote. Okay. Right. So that's my first part of the graph. After my asymptote, then you can see the curve is decreasing again, my apologies, decreasing towards my point of inflection, and it goes to 0, then it decreases again, so the whole graph is decreasing. But again, it has to reach my stationary point, so it's basically going to start underneath the x-axis again, because again, if it's underneath the x-axis, it has to be negative because it's decreasing, but it has to reach my stationary point on the x-axis. So actually, it's going to sort of, we're going to start at my asymptote, and it's going to touch my stationary point, and it's going to come back down again. Okay, something a bit like that. Okay, so it's like a inverted quadratic graph, right? So that's that is my sketch for part C. So I'll get rid of all that now. That is my derivative function sketch. So hopefully you start to pick up the idea now by considering that when the graph is decreasing, the derivative has to be in the negative on the negative part of on my graph, right? It has to be underneath the x-axis, on the negative y-axis. Because when the graph is decreasing, again, the derivative is negative, and then if it's increasing, it has to be above the x-axis, because that's when it's positive. Okay, I'm going to look at one more type of example of this, and we've got this sketch here. Okay, so we've got two asymptotes here, y is equal to 4 and y is equal to -4. Well, think about it. If y equals 4, then the derivative of that, we can differentiate that will go to 0. Likewise, if y is equal to -4, then my asymptote would also be 0. So that means my asymptote will then be y is equal to 0. So I can make a note of that. So so y is equal to 0 is going to be the x-axis, right? That's y is equal to 0, right? Okay, so firstly, I don't have any stationary points in this example. There's no stationary points, so nothing will be on the x-axis, which makes sense because it's, in this case, it's the asymptote. But anyway, But there are no stationary points, so nothing be on the x-axis. So let's consider the decreasing and increasing parts of the graph. Well, it's just decreasing, right? It's going down and then going down again, right? But notice more specifically at either end of the graph, at this end and at this end, they're both tending to the asymptote. They're both leveling off. So both at either end of my graph, they need to be tending to 0, because that's what the gradient is flatlining at either end of the graph that I've circled. Because again, it's leveling off. The gradient has to be 0, well, tending to 0 at either end. So that means on the negative axis, and it's decreasing, right? So it's basically going to look like this, and then it shoots back tending towards 0. Okay, and that will be my graph. Because again, it'd be negative because it's decreasing, right? It's going down the whole way through. But at negative infinity, right, and at positive infinity, they're both tending towards the gradient is leveling off, so they both will be tending towards 0. Okay, so that is graph sketching. So we're going to look at one more example exercise question here. Okay, so we've got this function here. F of x is equal to x plus 1, x minus 4 squared. Firstly, we need to sketch the graph y is equal to f of x. Okay, so well, actually, this is kind of a standard sort of graph we can sketch. We looked at this in chapter 4 when we looked at sketching cubics, right? So firstly, I note it is a cubic because this we're going to get x cubed out of this expansion, right? So we're going to get x from here, from that bracket, and this is x squared, right? So x squared and x will be x cubed overall. So it's going to be a cubic, and the cubic is a positive one because I'm going to get x cubed as my x cubed, right? Just 1x cubed if I expanded it. So it's going to have that sort of shape, right? So now I know what type of shape it is. Then I need to plot my y-intercept, right? My y-intercept is going to be when x is 0. So if I substitute that into my function, so f of 0, that's going to be 0 plus 1, that's going to be 1, times 0 minus 4 squared, that'd be plus 16. So 16 is going to be, let's say, up here. Okay, that's my y-intercept. Then I need my roots. So my roots, that's when f of x equals 0. So that means x plus 1, x minus 4 squared equals 0. So each bracket equals 0, right? So x is minus 1, x is 4. So I can plot them here. So minus 1 and 4. Okay, cool. Okay, so before I sketch my graph then, before I sketch my graph, there's two things I need to consider. Firstly, what type of roots do we have? Well, this one, x plus 1, that would be x equals minus 1. That's going to be a single root because it's just a single bracket. So it's just going to pass through it at that point like this. However, x minus 4, which is x equals 4, that root here is going to be a double. It's a repeated root. It's a double root because the bracket is squared. So what's going to happen is my graph is going to touch the root and come back up like this. It's not going to pass through it like that. It's going to touch it. Remember, we looked at that. All of this is basically recap from sketching cubics. We looked at examples just like this. So hopefully this should be a bit of revision. Hopefully it'll come back. But there we are. But the other thing we can do now is we can also furthermore consider the stationary points, right? So we know that f of x is equal to x plus 1, x minus 4 squared. So then that means if I expand it, so then I can differentiate, well, that'll be x plus 1 And then I need to expand this, right? X minus 4 squared. That would be x minus 4, x minus 4. Then I can expand this triple bracket. So that would be firstly x plus 1, x minus 4. That would be x squared. Minus 4x add x. That would be minus 3x minus 4 times by x minus 4. So that will get me x cubed minus 4x squared minus 3x squared add 12x minus 4x plus 16. And so if I collect the like terms, I'm going to get x cubed minus 7x squared plus 8x plus 16. Okay, so then if I differentiate, then I'm going to get 3x squared minus 14x add 8. Okay, if I differentiate, so then the stationary points, that's when f dash of x equals 0. So I can solve that equation as a quadratic. Okay, so then if I if I then solve that, let's say via the formula, x is going to be 14 plus or minus the root of minus 14 squared. Take away 4 lots of 3 lots of 8 all over 2 times 3. And so if I put that in a calculator, I would get x is 4 or x is equal to 2/3. Okay, cool. So that's my stationary point set. So okay, so then if I find the coordinates then of this, so that's the x coordinate. So as a point, remember a point is xy, a coordinate. I need the y value, right? So I need to substitute these back into my curve. So remember then y, or f of x is equal to x plus 1, x minus 4 squared. Was that right? No, x plus 1, x minus 4. My apologies, other way around. So then if I substitute these values in, I get the y coordinate. So if x is 4, then y is going to be 0 at 4 add 1, 4 minus 4 squared, which will go to 0. Okay, so that means we have the point 4, 0. Then if we substitute x is so at x is 4, at x is 2/3, then y is going to be x plus 1. That's going to be 2/3 plus 1. Then 2/3 minus 4 all squared. If I put that in the calculator, I get 500 over 27. Okay, and that doesn't have a nice decimal, so I can't just write it as a decimal. So that's it. So that means that coordinate is going to be x is 2/3, y is 500 over 27. Okay, so I've got my stationary points. Now you don't have to then work out if they're minimum or maximum, because we know what the shape already looks like, because we know what a cubic looks like. It's going to look a bit like this because it's a positive cubic. So then if we combine all that together then, so we'll add on my stationary point after this, but again recall then that my root, but this is a single root, so it's going to pass through -1. Then this is a double repeated root or factor, so that before it touches. So it's going to look something like this. So it's going to shoot up and pass through 16. It's going to come back down, then touch, and then shoot back up. And that's what my cubic, oh, a bit rough that was at the end. Let me sketch it again. There we are. I'll take it. Okay, so that's what my cubic is going to look like. Now, obviously we notice we've got a stationary point here and also a stationary point here, which is also at my root because it touches the root. So obviously we know this point is 4, 0. That's my first root, stationary point. It's going to be a minimum, right? This point is going to be a local maximum, right? This point up here. But how do we work out that coordinate? That's why we differentiated it. Remember that's going to be my other. That's going to be this stationary point here, right? When x is 2/3, y was 500 over 27, and that would be my stationary point at the top of that little hump there, right? And yeah, so now that's the cubic, right? So yes, so now we can use stationary points to add on a bit more detail to my graph, so I can label what the stationary points are as well to give a more detailed sketch. So there we are. So apart from that, really most of this should be a recap from chapter 4 when we looked at graph sketching. So this shouldn't be too unfamiliar, but now we can additionally label our stationary point as well. Okay, so that's my graph. Then part B, we now need to sketch y's f dash of x. Okay, I'm probably gonna do that up here because I've got really no room. I've got no room underneath. It's just full of working out. Anyway, so it's going to have x and y. So this is going to be my gradient function up here. Now again, we actually do know what the graph is in this case. Y is x plus 1, x minus 4. You could differentiate, which we've already done actually. We did differentiate. We got this, what was it, this quadratic here when we differentiated. You could sketch that, right? But again, you'd have to faff about with turning points and stuff like that, and you know, finding the turning point, finding the roots, finding the y-intercept, doing all that and sketching it. Or you could just look at my original graph and then do what we just did and consider when the graph is increasing, when it's decreasing, and where the stationary points are. So, right. So first of all, as always, we're going to consider the easiest thing to first take into account is where the stationary points are. So firstly, it's when x is 2/3. On my gradient function, f dash of x. So if this is y equal to f of x, then my stationary points has to be roots, okay? Because it's equal to 0 for the gradient function, right? So 2/3 for x. I'll label it here, and also there's another stationary point at 4, so it's going to be over here somewhere, right? So those are my two roots now. Now I need to consider when the graph is increasing and decreasing. So before my first stationary point here, it's increasing, right? It's going up, as so. Okay, so what that means is then if it's increasing, then the derivative has to be positive before the first stationary point, right? So it has to be above the axis, above on the positive part of the graph when it reaches the first point here. So it's going to come down like this, right? Okay, then after that point, it's going to go down. Okay. So after that, and then it reaches the second stationary point. So between the two stationary points, between the two roots here, it's going to go down and then reach the second point. So it's going to go down, then it's going to come back up so that it does hit the second point as well there at 4. After that then, it then increases again, right? So it goes up after the second point at 4. It increases indefinitely after that. So it's just going to go up again, okay? And that's my graph. Cool. That is my derivative graph. And again, that makes sense because we get a quadratic. A cubic differentiates to a quadratic. So there's my graph. Now, obviously, the only without trying to find the expression f dash of x, we can't really find out what the stationary point or the y-intercept is. We only know what the roots are. We don't have enough information for that. But that's what part D is going to look at. Okay. Anyway, so that's part B. We sketched the gradient function. Then part C, we need to show that f dash of x is this. So we need to actually compute what the derivative is. We sketched it, now we need to work out what it is, okay? We already did work out what it was, right? In part B, we saw that it was 3x squared and minus 14x at 8. Do I have any room? Okay, f dash of x is 3x squared. What was it? Minus 14x at 8. Now, what they want me to show is we need to show that it factorises to this. So we just need to factorise it, really, okay? Really, at this point, there are many ways you can do it. You can try and find the roots and then use factor theorem. But I'm just going to go back to basics and sketch it using what we looked at in the very first chapter, the AC method. So what we're going to do is we're going to consider two numbers that multiply not to get 8 but to get 3 times 8, which would be 24, and add to get minus 14. Then we consider the factors of 24. So 24 and 1, do they add or take away to get 14? No. What about 12 and 2? Yes. If I add them, I can get 14. Obviously it's negative, but don't worry, we'll just make one of them negative, or two of them. Okay, so now, to get minus 14, I need to make both of them negative, right? And that makes sense, because then minus 12 times minus 2 is plus 24. And they add to get minus 14, so that's my two factors. So this tells me then, because it adds up to minus 14, this tells me how to split this 14x up. I can then rewrite this as 3x squared minus 12x minus 2x add 8, right? That's the method we looked at. And then we can just factorise the two terms in this way individually. So if I factor 3x squared minus 12x, that'll be 3x lots of x minus 4. Then I can factor a minus 2 out to get x minus 4 as well. And what do you notice? X minus 4 is common factor, so I can factorise it out of everything to get x minus 4, then 3x minus 2. So therefore f dash of x is x minus 4, 3x minus 2. And I believe that should be what, yes, that's what they got. Okay, cool. Then part D says use the derivative to determine the exact coordinates where it cuts the coordinate axis. Okay, so we already know the x-axis is 2/3 and 4. That's where it cuts the x-axis of my gradient graph. But then I need to find the y-intercept. So I'm going to do all that then. So I need to find the coordinates of the gradient function where it hits the x and the y-axis. So we know then that my gradient function is x minus 4. Well, actually, we know it's 3x squared minus 14x add 8, which factorises to x minus 4 to 3x minus 2. Right? So firstly, my roots, right? That's when the derivative is going to equal 0. So we're considering the roots of the derivative function. So that's when each bracket equals 0, right? So x minus 4, 3x minus 2 equals 0. So that means x equals 4 or x equals 2/3. Well, what do you know? That matches, that reaffirms what we've got over here. My two roots of my gradient function are 2/3 and 4. So great, that's great news, right? So that's my roots. Then my y-intercept is simply going to be when x is 0. So that means f dash of 0, if I plug in x is 0 into here, all my brackets, that's going to be 0 minus 4, x minus 4, 0 minus 4, then 3 lots of 0, so it's 0 minus 2. If I put that in a calculator, I should get positive 8. Yes. So that means that the y-intercept that is going to be y equals 8. Okay, or the coordinate 0, 8. Okay. So then overall, the coordinates, so let's go back to the question. So we found the roots and the y-intercept now. So the coordinates where the gradient function f dash of x cuts the coordinate axis. So what's the coordinates where it cuts the axis? So coordinates where f dash of x cuts x and y axis are, well, firstly my roots are 4 and 2/3, so when x is 4, y is going to be 0, and when x is 2/3, y is 0, right, that's my roots. So if x is lows, x is 4 or 2/3, then the root means the y has to be 0, right? Then my y-intercept is 0, 8, and that's when it cuts the y-axis. And there we are. Cool. Okay, and that's it, right? That is it. Okay. This topic, again, I don't think I've seen this topic come up in an exam before, but there's always a first time, right? But yes, hopefully now you're a bit more confident in being able to sketch what the gradient will look like given the original graph by considering the stationary points and the increasing and decreasing parts of the function. Okay. So yeah, I'll see you next time.